Hi, welcome to the pre-lecture on analysis of variance for regression. Remember last time what we did is we looked at these test statistics, the Z and the T, test statistic, to test the null hypothesis that in a simple regression with one slope, to test the hypothesis that the one slope is 0 against the alternative that it was non-zero. Or that was the two-sided alternative. You could also have a one-sided alternative saying it's greater than 0 or less than 0. Now, so the idea was, is there anything in this model at all? You know, is this slope, can we make any prediction of, for example, we were talking about final exam scores from midterm exams. Does a midterm exam, this slope here, if it was a 0 slope, that would mean that knowing somebody's midterm tells you nothing about their final. So that's what we did last time, and we developed these two test statistics. But looking ahead to multiple regression, where we're going to add more predictor variables. For example, we might want to predict final exam scores not just from your midterms, but maybe from your homework, or maybe from what section you're in as well. We want to make a more accurate prediction, so with more variables, more predictor variables. And so we need a new test statistic besides these to do that. Because just because some of the, for example, let's say we wanted to, we have multiple predictors and some of the slopes might be positive, some might be negative. We won't be able to boil it down to a single signed number like a Z statistic or a T statistic. We'll have to look at the collective effect of all the slopes together. So this is similar to what we did before when we were comparing multiple group means. We had to use a statistic based on analysis of variance. We ended up with the F ratio. Sorry, the F ratio. And we're going to do the same thing here. So we're going to use analysis of variance as a way to assess the effect of the collective effect of all the slopes. But before we do that, we can actually apply it to simple regression, and it'll be easier to understand. And we can then relate the statistic that we develop based on analysis of variance and see how it's going to be the same as the square of these two statistics. All right, so that's where we're going. So let's recall what we did back with looking at ANOVA, analysis of variance comparing group means. Okay, so what ANOVA does is it breaks up the variance of the y's, what you're trying to predict, into two pieces. One that's explained by the model, the variance of the model, plus the variance of the errors. So that's what we did last time. We did that last time with ANOVA and comparing group means. And the way we did it with ANOVA, and ANOVA comparing group means, we're going to compare that, comparing multiple means. We're going to compare that to using analysis of variance for regression. So here's ANOVA for comparing group means, and now we're going to look at it for ANOVA analysis of variance for regression. And they're really, really similar. We're going to split the variation of the y's, the quantitative variable we're trying to predict, let's say it's finals, into two pieces. And the model here for comparing means would be predicting what people got on the final by some group membership, let's say what section they're in. That would be, we would be comparing the means of the exam scores in different sections. And then there'd be scatter within each of those groups around the mean. So let's write that down. So what we did with the ANOVA, we said the variation of the y variable is going to be equal to the variation or the variance predicted by what? By group means, by the group they're in. It's kind of like stereotyping. If they're in one group, we're going to predict that their final exam score is going to be the group mean. Yeah, just ignore everything else, just whatever group they're in. All right? And then we have the variance left in the scatter, or the scatter within the around the group mean. The within group scatter. So how do we say this? We said the variance of the y's, which is SST divided by n, but we can do this, SST divided by n, is equal to SSB, the between group variance divided by n, and then the within group variance. And probably most people just divide everything through by n, so they call it sum of squares and not variance, variability. So that's where we're at. Now let's do the same thing here. So for regression, what are we going to do? We're going to say, let's say we're predicting final exam scores by now a quantitative variable instead of a categorical one. So it won't be by group means, it will be by something like exam scores, some quantitative variable. And our model would be a regression line. So it would be the variance predicted by the regression line, by our sample regression line. So we'll, that's the model, we'll make some prediction based on the regression line, and then there's variance, there's scatter around the regression line. So the variance left, the unexplained variance left in the scatter around the regression line. So this is like, the standard deviation of the errors around the regression line squared. Okay? So now we have SST again, divided by n. That's variance of y. And here we have what's called the sum of squares. Some people call it sum of squares R for regression, but in this class we're just going to call it sum of squares model. Plus, and this is our sum of squares error. And again, typically everybody multiplies through by n, and we just get this. And we call it sum of squares, or variability instead of variance. All right, so that's where we're at. Now, what did we do? Last in here in comparing means, we looked at a tweaked ratio of this. So it's basically, this is the strength of the model, right here, strength of the model, and this is sort of the strength of the errors. And the ratio of those two, the F ratio, is the ratio of the strength of this model divided by, it's the ratio of the strength of the model to the strength of these errors. But it's adjusted by their degrees of freedom. So it's the SSB divided by its degrees of freedom. And remember, that's the number of groups minus 1. And SSW divided by its degrees of freedom. And that's n, the number of observations, total number of observations, minus the number of groups. Another way of looking is, people call it the mean square between over mean square with it. So we have that. So we're going to do exactly the same thing here. And we're going to develop an F statistic, a test statistic, to test the collective effect of our regression model of all the slopes in it. Here we only have a single slope, but you could have multiple slopes. And it's going to be the same thing. It's going to be sum of squares for the model divided by its degrees of freedom, which is, instead of the number of groups, it's the number of parameters in the model. So parameters in the model, in which case our model is what? For a single group, it would be what? So we have two parameters. So P equals 2. We're estimating two parameters. So it would be P minus 1, 2 minus 1 for simple regression, over sum of squares error, which is just analogous to that. It's N minus P. Okay, and so another way to look at this, if we simplify this, we get SSM over SSE, and then tweaked by N minus P over P minus 1. And here, it's the same thing. When we simplify it, we're going to get N minus G over G minus 1. All right, and these will be our test statistics to, it's going to be analogous to the test statistic, the T statistic. And you'll be able to see that much more clearly if I rewrite this part of it. So this part of it right here, this assessment of the strength of the model over the errors, can also be written as R squared over 1 minus R squared. And I'll show you why in a minute. So we can rewrite this as our correlation coefficient squared over 1 minus R squared times N minus P over P minus 1. We could do the same over there too, but we've defined our correlation coefficient in regression, so it's easier to understand here. All right, so let me explain that. Okay, so you may wonder why this is the same thing as this. How does R squared relate to this? Well, back on page, I think it's 126 in our notes, we talked about R squared as being the coefficient of determination. And we talked about it being the proportion of the variation of the variability in the y's that's due to the model. But you might not remember it so well, so we talked, here's what you probably do remember, that the standard deviation of the errors, which is a measure of the scatter around the regression line, that is equal to the square root of 1 minus R squared times the standard deviation of the y's. Now this scatter around the regression line, this is the standard deviation. When we square it, this is the variance of the errors, right there. That's the variance of the errors. And so we'll square both sides, so we get 1 minus R squared times the standard deviation of y squared, which is the variance of y. So that's what we have. So we see right here that our variability of the errors is 1 minus, the variability of the errors is 1 minus R squared is the fraction of the total variability that's in the errors. What is the variance of the errors? That's SST, right? I mean SSE, excuse me, errors, sum of squares errors over n. And that says that this is equal to 1 minus R squared times, and what's the variance of y? That's S, the total variation over n. So we get this relationship, we can multiply through by n, so we get this. So, if 1 minus R squared times SST is SSE, then SSM has to be R squared times SST, because they have to add up to 1. So there we have our relationship here. So instead of writing SSM and SSE right there, we can write R squared over 1 minus R squared and cancel out the SSTs. So SSM divided by SSE is equal to R squared times SST divided by 1 minus R squared times SST. So now you're probably wondering, how does this little r squared, the correlation coefficient, relate to this big R squared? And for simple regression, they're exactly the same thing. They're exactly the same thing. The advantage of this R squared with a capital R is that it's actually the correlation coefficient of your the predicted y's and the actual y's. Remember, correlation is only defined on 2 sets of numbers. So here we're fine. Y and x, we just have 2 sets of numbers. But when we add more slopes, we're going to have 3 and more sets of numbers, and there's no way the correlation is defined on 3 or more sets of numbers. So what this capital R is the correlation coefficient between your predicted y's and the actual y's you have. And for simple regression, they're the same thing. Okay, so that pretty much explains that. So let's use this. Why am I why did I even explain this? Is because R squared is given to in all regression analysis. And it's a very easy way to think about the strength. You know that think of it as the correlation coefficient. And it's a very easy way for you to remember. This describes the strength of the model. This is the strength of the errors. And that ratio is the crux of our test statistic. So let's do a problem that I think will make much more sense. Hi everyone. So this is an example where we can use analysis of variance to test whether a slope is 0 in some linear model. We're starting off with just one slope here. All right, and let's say that you know the sample size is 20, and you know the standard deviation of the y variable is 10. And let's say you know the correlation between the x and y's are 0.5. Okay? Well, we could easily do our formula and solve this very quickly. The formula we just got, and to get this F statistic, to test whether, to get a p-value to test this. So we can do it that way, and then I can also show you how you can use this, where this same information would be used to fill in an ANOVA chart. So the way we just did it was we said, okay, so F, our F statistic, would be equal to R squared, right? Which is the same thing as little r squared. So we'll say R squared over 1 minus R squared, adjusted by the degrees of freedom here. So remember, it's, the numerator degrees of freedom is just going to be the number of parameters 2 minus one of them. So it's going to be this one, the numerator, is going to be p minus 1, and 1 minus r squared, the denominator is going to be n minus p degrees of freedom. So that's the same thing as r squared over 1 minus r squared times n minus p over p minus 1. And the reason I like to look at it this way is because it's so easy to remember. Because right here, this shows you the strength of the model is. What the model is, the stronger your correlation coefficient is, the better your model. The higher this is. And the bigger your sample size, the more evidence you have that if there is some effect here, the more evidence you have of that effect. The bigger your sample size, the more accurate reflection it is of the population. Remember what we're doing here. We have a sample from a larger population, and we see this in our sample of 0.5, but we want to know if it holds up in the entire population. Well, if you only have a sample of 3, you're not going to be as sure it holds up in the whole population as if you have a bigger sample. So what's nice about this is this numerator, when you think about it this way, is a reflection of the strength of our model, whereas the denominator, the 1 minus r squared, is a measure of, obviously a measure of the weakness of the model or the strength of the errors. And along with this p minus 1, because the more parameters you have, the easier it is to fit a model to your random sample, even though it might not hold up in the whole population. Think about it. If you have a sample size of n and you have that many parameters, you could perfectly fit your particular sample. If you have as many equations as many variables as you, parameters here as you have points. So so basically this is a very nice way. This is the strength of the model. The numerator, and this is the strength of the errors. And the ratio when the null is true, since the models, when the null is true, that there's no model at all there, that it's just, the null is that there's no slope, there's no model, there's just, when the null is true, then the strength of the model and the strength of the errors are going to be equal, so they're going to be about equal. So this f would be about 1 when the null is true. So if you get a statistic much bigger than 1, you're going to reject the null. Okay? So we have this. So this is really easy to solve just by the formula. We have r squared, which is 0.25 over 0.75, right? That's 1/3 times n minus p. So n minus p is 20 minus 2, so that's 18 over the number of parameters is 2 minus 1 is just 1. So this is what? 1/3 of 18, so 6. So we could get a p-value by looking up on the F table, F with 1 degree of freedom, p minus 1, 1 degree p minus 1, and n minus p. This statistic is distributed as an F statistic with this many degrees of freedom. So in this case, p minus 1 is 1, and n minus p is 18. And we've got to see this, and then we'll look at the F distribution. Is going to look like it's just always positive, and we'll see how far out 6 is. Okay, so looking on an F table, I found that, okay, when the null is true, the probability of getting this big an F or even bigger is really small. This area here is only about, and that's our p-value. I'm going to get a better pencil. Our p-value is about 2.5%. Now this F distribution is all positive, so it's like a two-sided test. It's a two-sided test, so the p-value is less than 2.5%. So we would, if we were using, so the probability that we'd see this large enough, if the null was true and there was no correlation at all in the population, is very small, and we would reject that at 5%. Okay? So now, you're probably wondering how this all matches up with this ANOVA, and how it all matches up. All right. Now, first of all, our sum of squares total, that's SST. We can get that from this. All right? Remember, that that's the standard deviation. So if we square it, SDY squared, SDY squared, which is the variance, is going to be 100, right? But this is the variance, so that's SST over N. So I have to multiply that. If I multiply that by N, so N times SDY squared is is equal to the SST. So 100 times 20 is 2,000. All right? So we've got that. And now, remember that, okay, so SSTM and SSE have to add up to that. And remember what we said, that SSM is R squared times SST, and SSE is 1 minus R squared times SST, and together, R squared plus 1 minus R squared times that is SST, right? R squared plus 1 minus R squared is 1. So, R squared is the square of that, so it's 0.25. So then we're just going to say, okay, so this is 0.25 times 2,000, and this is 0.75, 1 minus R squared, times 2,000. So this is 500. That's 500. And this is 1,500. And sure enough, they add up. All right. So now we know that. And what are the degrees of freedom? Remember, the total degrees of freedom are n minus 1. So in this case, we have 20 minus 1. There's n. So we have 19. And how do we divide this up? The degrees of freedom are going to sum up. This is exactly like what we did for ANOVA for groups. And so this is the model, remember, is based on how many parameters in the model. We have 2 parameters in the model. All right? But it's really only the slope we care about. This intercept we're just subtracting off. We want to know how, basically the variability is how far above or below average. So this doesn't really matter. So we're just looking at the one parameter here, p minus 1. If we had 2 slopes, we'd have, it's always the number of slopes minus 1, the number of parameters minus 1. So here, 2 minus 1 is 1 degree of freedom. So we know this has to be 18, because they have to add up. But we also know this is n minus p. So that's 20 minus 2. All right, so we make sure those add up, the degrees of freedom here. Now, remember what you do to get the F ratio is what? The mean square model over the mean square error, or mean square between over mean square within. So the mean square is just the sum of squares for the model. The mean square model is the sum of squares for the model divided by the degrees of freedom. And the mean square for the error is the sum of squares error divided by the degrees of freedom here. So what's this one? This one's just 500 divided by 1. And what's this one? This is 1,500 divided by 18. 83.33. So our F statistic is equal to the mean square model, which is 500, divided by 83.33, which must be equal to 6. And I'm sure it is. So we get the same answer there. And it's obvious to see from algebra why we got it. because we have SR squared over SST divided by 1 minus R squared divided by SST divided by the degrees of freedom. So that's all we're really doing. Okay, now one last piece of information I want to show you is, no, first off, the reason I could do this is because I was given R and the standard deviation here, right? In class, you're going to have to do all that from scratch, but you're not going to have 20 points, you're just going to have 3, just so you can see how it works out. So in class, you're going to do this whole problem, you're going to have to do it from scratch, you won't know R, and you won't know the standard deviation of Y. You're going to figure all those out directly, and that's what you're going to do, but we're not going to make you do it with 20 points, okay? And in all the regression printouts you see, you'll be given R squared. So it's a nice way to look at it. Now, let's tie it right. You're probably thinking, well, she went through all this, right? All this stuff to get a test statistic that we already could do using the t. So previously we could have tested a single slope here with the t statistic, and let's see how this F statistic compares to the t. So the t we talked about at the beginning, the t statistic is R over the square root of 1 minus R squared times the square root of n minus 2. So let's see how that matches up with this right here. Well, n minus 2, in this case, with 2 parameters for just a single slope, R squared over, this was a 2, and this was a 2, for the number of parameters. So can you see how the t squared, if we squared the t, we'd get R squared over 1 minus R squared times n minus 2 over 1. So for one parameter, for 2 parameters for simple regression, where there's just one slope, the t, so t squared is equal to f when you have 1 degree of freedom in the numerator, when you have just one slope. So whatever, so it's like t squared with n minus 2 is equal to, that's the same statistic, and it will always give you a 2-sided. If you square it, it's always positive. And so those two are equivalent. Okay, that's it.